Hey everybody. So this is learning target 2, continuity, a little bit more meat in the bones in this learning target than the first one, and including some algebra. So first of all, we just had to get a basic idea of what continuity is. But before we do that, you really do need to know how to use your calculator. And I know not everybody has a calculator, but you can download a free calculator. Let's see. This is I got two on my phone right here. Just go to your app store and do a search for TI-84. There's at least two out there, and play around with it. But TI-84 is really taking over the world. Now, then you need to know how do you actually graph these things, because like right here, I don't. Desmos is amazing, but you need to know how to use your calculator. So you need to be able to graph something like this on your calculator and find these maximums and the relative minimum. You need to find that on your own. And your calculator can do that. Do you know how to do that? Well, on my website, Mr. Scarlett, schs.weebly.com, underneath Honors Pre-Calculus, Unit 1, there are, scrolling on down to the solving learning target 4, there are two videos here. It's going to take a second to pop up, but there are two videos here that describe how to do that if you don't know how. The easiest thing to do would be for you to find somebody who knows and ask them. That's going to be the best. But if you're a real extreme introvert like myself, you're going to have to look at these videos. One for the Inspire, one for the 84, and there you are. But know how to graph these things in your calculator and find the maximums and the minimums. Okay, continuity. Continuity, a graph is continuous if you can draw it without lifting your pencil. This is continuous all day long. I can draw this purple graph 100 times again without ever lifting my pencil. This graph is not continuous. And the reason why it is not continuous is because, well, I would have to lift my pencil to draw all these parts. And the breaks occur at x values. You have to think in terms of x values as usual. So this graph in particular is discontinuous 3 times, starting from the left. When x is -6, if you were to graph this, there's a hole right here, and it's displaced down there. So that's 1 point of discontinuity. Continuing on, there's another point of discontinuity when x equals -1. There's a vertical asymptote here. And then continuing on, there's another point of discontinuity when x equals 4. So there are names too. A hole would be called a removable discontinuity, and a vertical asymptote is an infinite discontinuity. More on that right now. So here's another graph, and this one has 4 points of discontinuity. I see one here when x is -5, one when x is 0, there's a hole, when x is 1, and when x is 6. So these are all points of discontinuity. Now the one at x equals 0 is a hole, a removable point, but the other 3, they're different than the asymptotes. They're not vertical asymptotes, but rather we call them jumps. And they only occur when in a piecewise function. It's the only time a jump will occur. And the reason why is, the reason why they're called jumps, I guess, is because there's a finite amount of y values between the two sections. Whereas in asymptote, there's an infinite amount. So here's another graph. This is the original graph you saw from the last slide. And there's when there's only one y value missing, one single y value missing from the graph, making it continuous, then it's called a hole or a removable point. But when there are an infinite amount of y values to get to one section of the graph to another, that's a vertical asymptote. Okay, now here's what you'll have to do. One, you'll be given a graph, and you have to tell me the points of discontinuity and what type, and then you'll have to do it algebraically. Algebraically is, of course, more difficult. So here we have yet a new graph, and scanning from left to right, I see I've got a point of discontinuity at -6. There's one here at -1. There's another one here at 3 and another one here at 6. So that's 1, 2, 3, 4 points of discontinuity. Well, come on. -6 and +3 are points of discontinuity. They are removable discontinuities, so holes. X equals -1 is an infinite discontinuity. That's always a vertical asymptote. And the final one, x equals 6, is a jump. This looks like there are only 3 y values separating these two pieces, but these two pieces are separated by an infinite amount of y values. Algebraically, how can it get more difficult? Here's how. We need to do this algebraically. So first of all, this is one function. It's not a piecewise function. So that means if this has any points of discontinuity, it'll be x values that make you divide by 0. And they will either be holes or vertical asymptotes. That's the only two type. The only time you would get a jump is if it were a piecewise function. So again, this is not a piecewise function. So if it does have a point of discontinuity, it's going to be an x value that would result in division by 0. Always looking for these x values. So it makes all the sense in the world to try to figure out what x values will make you divide by 0. So factor this into x plus 3, x plus 2. And oh, by the way, the domain, the domain should kind of always be in the back of our minds. Here, the domain for this function is every real number except for -3 and -2. So here's that domain in interval notation. But -3 and -2, those are the 2 points of discontinuity. They are the only 2 x values that make you divide by 0. So if we were to graph this, there are only 2 points of discontinuity. But that's only half the battle. You have to tell me what kind they are. So you have to keep on simplifying, factor the numerator, and you notice that the numerator and the denominator both have an x plus 3 in common. So those factors are removed. So x plus 3, the x plus 3, the one that got removed, that is connected to the removable discontinuity. So in other words, the hole. There is a hole at -3 when x is -3. And the other one, when x is -2, the other one is a vertical asymptote. But the one that got canceled out, I think this was covered in Algebra 2, the one that got canceled out, or in other words, removed, is a hole, a removable point. But now we need to go one step further. Where exactly is the hole? I know where the x is, but what about the y value? How in the cuss word would you even find the y value? You would find the y value by plugging in -3. You can't plug it in here because you would divide by 0. You have to plug it in over here after you've removed the factor. So you plug it into what's left over. So -3 minus 4 divided by -3 plus 2, and you get 7. So now there is a hole at -3, 7. And of course, there was that vertical asymptote at -2. So when you practice these, this is you really are learning a lot about these functions. This is a rational function, and there are 2 points of discontinuity. There's a hole at -3, 7, and a vertical asymptote at -2. And let me show you what that graph looks like. Here is that function. And of course, I hope it's obvious that there's a vertical asymptote at -2, but not so obvious of a hole at -3, 7. Here's -3. Here's 7. It should be somewhere around here. And if you drag along the graph, there it is. -3, comma, undefined. That's my wife. I'll have to wait. -3, comma, undefined. So there is indeed a hole, and it's at -3, 7. All right. Okay, these are two piecewise functions, and the directions are determine if each function has a point of discontinuity. Well, they're both piecewise functions, so now we're really going to flex your mental muscles here. We're not going to look at the graph at all, but just what do we know about this? I got an absolute value function here and a quadratic function here. Absolute value function here, quadratic here. Okay, sorry about the delay. We have a piecewise function, two piecewise functions, and are they continuous or are they not? Well, we've got an absolute value part and a quadratic. And the absolute value part occurs to the left of 3, including when x actually is 3. And then the quadratic occurs to the right of 3. So imagine your head, some sort of absolute value to the left, and then a parabola to the right. And 3 is like the boundary. 3 is like the borderline that separates them. Realize the domain is all real numbers. Every number is accounted for. Some of them are on the absolute value, some of them are over here. Well, how can I figure out if this is continuous? The absolute value is continuous for sure. It's just a v. I could draw a v without lifting my pencil. And the quadratic is continuous. I could draw a quadratic without lifting my pencil. So this v would be upside down, the quadratic would be over here or something like that. And the only way that they would be continuous is if the quadratic happens to pick up precisely where the absolute value left off. If when x is 3, the parabola is way down here, then there's a jump. Or when x is 3, if the parabola is up here, there's a jump. Only when x equals 3, when the handoff occurs, if they are precisely at the same y value, then it is continuous. So I hope that is clear enough to realize what we have to do. We're not going to graph this. We're just going to plug in 3 into this and see what the y value is. And then we're going to plug in 3 into this piece and see what the y value is. And if the y values are the same, then it is continuous. So let's see here. -2 times the absolute value of 3 plus 6. And 3 plus 6 is 9. The absolute value of 9 is 9. So it's -2 times 9, which is -18. So for the absolute value part, I know the absolute value leaves off a y value of -18. Now, where does the parabola pick up? The parabola is 3 plus 1 squared. And that's 4 squared. And 4 squared is 16. So the 316 isn't on this graph because x is greater than 3, but that's where the open circle would be. So again, the absolute value leaves off at -18, way down here, and the parabola picks up at 16, way up here. So they've got a finite difference of whatever 18 plus 16 is, 44 or whatever, or 34, I don't know. So needless to say, it is not continuous. So not continuous. There's a jump at x equals 3. That's what you need to say to get full credit using the proper terminology. And of course, without any work to support it, you're not getting credit at all. So here's my work, not continuous. What about this guy? Well, I've got a line that only exists from -6 to 10. Lines are continuous. So there's no question here. This part is continuous from -6 to 10. Here's another parabola when it's greater than 10. So what is first of all, the domain is everything from -6 to infinity. when x is greater than -6, all the x values are accounted for all the way up to infinity. So is this continuous? Well, let me draw some graphs again. Let's do blue. So here you got your line, 3x plus 4, and I've got my parabola that's kind of skinny, but it's to the right 6 and it's up 2. Well, the line exists from -6 to 10, and then it leaves off somewhere. Will that parabola pick up exactly where the line left off, or will it be up above or below it? And the only way to figure that out is to type in what x value. 10 is the key x value. So we're going to type that in. That's 34. So the ordered pair for the line is 10, 34. The what's it called? The line will leave off at the y value of 34. And then for the parabola, I've got 2 times 10 minus 6. Square that puppy, add 2, and that's 2 times, 10 minus 6 is 4. 4 squared is 16. And 2 times 16 is 32. 32 plus 2 is 34. So 1034. The parabola also leaves off at positive 34. So precisely where the line leaves off, the parabola picks up. So this is continuous. G is continuous. 100%. Last slide. Find all points of discontinuity for this function. And don't be thrown off by this plus 19. That plus 19 does not impact the x values whatsoever. There's not even an x next to it. It just takes this nasty rational function and raises it up 19. So how do I find all the points of discontinuity? You factor, of course. Points of discontinuity, remember, if it's not a piecewise function, then points of discontinuity occur for x values that would divide by 0, that would result in division by 0. So you factor x squared minus 9, and there are 3 points of discontinuity. Positive 10, -3, and -3. And then also factor the numerator so that you see what types of discontinuity there are. This factor canceled out. Oh, the domain, of course, just for fun. The domain includes all real numbers except for -3, +3, and +10. So after you cancel out the x plus 3, you're left with this, which tells us that there are vertical asymptotes, or in other words, infinite discontinuities at x equals 3 and x equals 10. Those are the 2 x values that make you divide by 0, and they don't cancel out. But the harder thing to find is the hole. There is a hole at -3, but then how do you find the y value? You have to plug it back into the function. You can't plug it in here because you can't plug in -3 because you would divide by 0. Only after you cancel that out with this new kind of reduced version, you plug in -3 into this to find out what the y value would be, like I show right here. So this just takes a little bit of work. Make sure you follow your order of operations. Use your calculator when you need to. And yeah, I did not do that. I just plugged this into the calculator and I got that. So there is a hole at -3, 734/39. That is a removable discontinuity. Hopefully that makes sense.